All right, guys, so the last page that we filled out here was solving logarithms, and that was the end of that chapter there. So if we turn the page, right behind that, we're not going to put anything. And around the next one, we'll put our table of contents. I guess I could have already had this set up for you, but, you know, we're recording now, so we're just going to go with it. And there we go. Oh, I'm going to have to find my tape later, though. Right after that, we are going to put this half sheet here, and then we have a book, which I have fold really quickly. And I guess while I do, I will grab my tape. I'll be right back. So in this new chapter, we are going to be talking all about rational functions, which a rational thing is just some number that can be written as a fraction. So we are dealing with some of my favorite types of numbers, fractional numbers. And then when we call it a function, that means it's going to involve variables. So it's going to have some x's involved in that fraction. So kind of main three things that we want to do with any new function is we want to know how to solve them. So kind of like with our last chapter, we are solving exponentials and logarithms. We also want to know how to kind of like mess around with them, like we were expanding and condensing those logarithms. So we want to know how to do that with fractions as well. And we also want to know how to graph them, which we did last chapter also. So for this one, the way I thought we would start is kind of how we mess around with rational functions. So when I say that, I mean we're going to be like following order of operations to take multiple fractions and do some stuff with them. So right behind this half sheet here, we will put our book. And then let's go back and add to our table of contents. So over the next couple of days, we are going to go through all the different ways that we can simplify fractions, which I mean, if you think about it, doesn't sound too bad. So simplify rational expressions, and we are going to be doing that. Let's see, we are on page 97, 98, and 99, I think. We might go up to 100, but we'll just wait and see. Now, when we talk about simplifying fractions, very basically, I might be dealing with one single fraction. So let's actually turn to page 97 for a second, or 98 rather. Really easy example of simplifying a fraction is, let's say I had something like 12 divided by 28. Now I could leave it like that. However, mathematicians like to simplify things if possible. And because we are dividing, if I can divide the same number on top as I have on bottom, then that's a 1. And so I don't really need that. So I can kind of rewrite this fraction as 4 times 3, because that's still 12, over 4 times 7, because that's still 28. And then because I have these 4s, they divide out to 1. And so my reduced simplified fraction is just 3/7. Now the big thing to notice here is I was able to divide those 4s out because they were being multiplied to another number. That's very different than something like if I had 12 plus 5 over 28 like this. I can't do the same thing where I change this 12 to 4 times 3 and this to 4 times 7 and divide out the 4s, because really what's happening here is I do have some hidden parentheses, meaning that I need to add the numerator first. And then once I've done that, I can't really simplify now because 17 is prime, so I can't split it up in any way to divide out a 1. So if there are addition or subtraction symbols in between, I can't really simplify one number with one number if I can't also do it with the other number, like the 5. I have to add those things before I'm able to divide the things out. I can only simplify when there's multiplication in between, not addition or subtraction. So the way that we take something that is a multiplication problem, the way that we take something that is an addition or subtraction problem and maybe change it so that it is a multiplication problem so that I can divide stuff out is, number one, we are always going to have to factor our numerators and denominators. So no matter what, if you have not factored or if you have not attempted to factor before you start dividing stuff out, then you can't divide stuff out. So just don't. So going back to this page here, just a couple of reminders on how to factor. There's lots of different ways, but the first thing that we always want to be thinking about is, do I have a GCF? And if I have a GCF, I definitely want to undistribute that, factor that out. And then from there, the way we factored was always dependent on how many numbers we had. So if there are 2 numbers, 3 numbers, or 4 numbers, we factor different ways. So our 3 numbers was like the X puzzle, or maybe our slide divide bottoms up. When we had 4 factors, that was kind of the factor by grouping, or the unboxing method. So we put everything in the box and then we divide stuff out of the box. So we had our 4x4 and all your numbers go inside and you do rows and columns. The last way that we had that we talked about factoring was when we had 2 terms, and this was kind of the trickiest one. It might just be a GCF thing, but then you might ask yourself, do I have perfect squares or perfect cubes? And each of those factor different ways. And so we kind of have to remember how to do that. So just another quick little reminder, what is a rational expression? It is a fractional math sentence without an equal sign. We are not solving, we're just simplifying. So there is no equal sign here. We are going to be rewriting things so that they look different, but we're not solving anything. And then when will we know that a rational expression is completely simplified? We will be done when we have fully factored and each common factor is divided out. So factor is something that is being multiplied versus a term, which is something that is being added. Okay, so trying to start easy here. This first example, on all of these, we have everything already factored. And I can tell because I'm looking at a big old multiplication problem on top, big old multiplication problem. Now the denominator here is a little strange, but like this one, this is overall a big multiplication problem. I have this number times that number, and this number times that number. So maybe we're going to start at the end and work our way back. So starting with F, on the numerator, I kind of have 4 numbers being multiplied, and on the denominator, same thing. So if any of those numbers on top are the same as the numbers on bottom, I can divide them out. So for instance, the 8 and the 2. They're not the same, but they do have a 2 in common. So I can divide a 2 out here and I'm 1. I divide a 2 out here and I'm 4. I can also divide these x's because they're the same, and x divided by x is just 1, so it kind of just goes away. The next term that I have on top, or the next factor that I have on top is x minus 3. and I have another one on bottom. So this x minus 3, the full factor, can fully divide out with this x minus 3. Now the last thing I have in the numerator is x plus 1, and that is not in the denominator. And so we've divided out everything that we can. And in my numerator, I have a 4 smushed up against an x plus 1. And then in the denominator, I have the 1, so I kind of don't need it. And then the x minus 2, which, since there's nothing else down there, I kind of don't need parentheses. And that is it. So I was fully factored. I canceled out my common factors, and so now I know I'm done. The only additional thing is that whenever we're dividing, we do have to be a little bit careful that we don't divide by 0. And because there is an x in the denominator, there is potential for that to become 0. So I have to say that x is not allowed to be some number. And I think the number that x is not allowed to be here is 2. Because if I plug in a 2 right here, 2 minus 2 is 0, and I divide by 0, and that would be awful. So we don't want to do that. So that is part of your answer, stating your restrictions. Okay, working our way backwards here. So looking at E, this is overall a big multiplication problem. A big multiplication problem. So this is factored. And the 5 and 15, I can divide out a 5. So 1 here, 3 there. These, however, are not the same. And so I cannot divide them out. And so my numerator is x minus 3. My denominator is 3 parentheses x plus 3. Now, I didn't mention this on the last one, but it could be very tempting to distribute that. And you could distribute that. That wouldn't be wrong. It just feels like extra work to me. So that's why I'm not going to do it. And then I want to say what x cannot be, because I do have x in the denominator here. And I think if this was negative 3, this would be 0. Multiplied by 3 would be 0, and that would be bad. So just to point out, I'm not really guessing. I am doing some math to figure out what x cannot be. I'm basically taking the denominator and setting it equal to 0, and then solving. And then saying, oh, nope, you can't be that. So that's kind of what we're doing here. And it's pretty easy to do these simple problems in my head. That's why I'm not writing it out. Okay, looking at D, this is a big old multiplication problem on top, big old multiplication problem on bottom. And so I can start dividing out common factors. So like the 3 can divide into the 12 4 times. X divided by x is just 1. And when I have 1y on top and 2y's on bottom, 1y can go away, but 1y will still be left on bottom because there were 2 down there. And so because my numerator is fully gone, I do need a 1 up there to hold the numerator's place. And then my denominator is just 4y. And I do have a variable down there, so I need to say, okay, y cannot be 0. Because 0 times 4 would be 0, and that would be bad. Okay, looking at C, we are still a big old multiplication problem, big old multiplication problem. So I'm looking for a factor of x plus 2 on bottom, which I have. And I'm looking for a factor of x minus 3, which I do not have. So I was factored, I canceled out my common factors, and now I just rewrite my answer. We got x minus 3. And then 2x minus 3. X cannot be 3 over 2, because I'd like add the 3 over and then divide the 2. Okay, this is a big old multiplication problem. This is not. So I should try to factor that, but I don't think that it will. Like if I look at 3x minus 1, they don't have anything in common. So I can't really factor that. And since I couldn't factor this, and I don't have an exact factor of 3x minus 1 on top, I can't divide anything. So this is already simplified. However, I do need to say like what x cannot be, because it still does have a denominator with an x in it, so x cannot be 1 over 3. And then last but not least on this page, A is a big old multiplication problem on top and bottom. So we can divide the 12 into the 60 5 times. And then I have 3 x's on top, 5 x's on bottom. So when I divide them out, I will have 2 left on bottom. So numerator is 5, denominator is x squared. Because x is in the bottom, I need to say that x cannot be 0, because if it was, that would be horrendous. That would be terrible. Okay, so now let's try something that are slightly harder because we have to factor first. Those ones were all nice. They were all factored for us. These ones are not, however, and I can tell because the numerator there is a big old addition problem, and so is the denominator, I guess, subtraction problem, but because it's not multiplication overall, that's why I can't cancel yet. So top one, I'm thinking X puzzle. So like what multiplies to 10 adds to 7. So 5 and 2. So I'm going to rewrite this as x plus 5, x plus 2. In the denominator, because there are only 2 terms, I'm thinking perfect squares or perfect cubes. And these are perfect squares. So when we have perfect squares, we get 2 binomials. And we square root each thing. So x and 2. One's a plus, one's a minus. So that we get 0 in the middle and a -4 at the end. So then I'm a big old multiplication problem right now. I'm looking for a factor of x plus 5 on the bottom or an x plus 2, which I do have. So those fully cancel. And we're left with x plus 5 on top, x minus 2 on bottom. X cannot be 2. Okay, so looking at B, the numerator, because it has 2 terms, normally I would think like perfect squares or perfect cubes, but they are neither. And so I'm actually kind of forgetting this step where I need to think about a GCF, which is actually what I have. So we have 2x, and when I undistribute that, we have x plus 3. Oop. Now my denominator, I have 3 terms, so I want to do the x puzzle. And this one has a number out front, so we're going to slide that over. So what multiplies to 6 adds to 7. And that would be 6 and 1. So we have x plus 6, x plus 1. But because I slid that 2 over, I got to divide that 2 out. When I can divide, I will. So x plus 3. When I can't, bottoms up. So 2x plus 1. So this factored to x plus 3. And then 2x plus 1. So looking at my denominator, if I had a factor of x plus 3 in the numerator, I could cancel it, so I can do that. And if I had a factor of 2x plus 1, I could cancel it, but I don't. That's just a 2x, so we have to leave that. So we have 2x on top, 2x plus 1 on bottom. X cannot be -1/2. Okay, let's try another. Looking at these last few examples here, we still have to factor. This is a subtraction. This is a big almost or addition. It's not multiplication, so I need to factor first. So looking at this numerator here, we have 2 terms. They do not have a GCF, so perfect squares or perfect cubes. And I think those are perfect cubes. And when we factor that, that's when we got the binomial trinomial situation, where we're thinking what times what is x to the 3rd, and that's x. And what times what is 27, and that's 3. And then we get our numbers from the 3 terms from the ones we just got, so we square it, multiply, then square it. Signs go same, different, positive. Now on the bottom, I should be looking for a GCF first, which I do notice that they have one, a 3. So then I have x squared plus 3x plus 9, which then I could try the x puzzle on that. So I'd be thinking like what multiplies to 9 and adds to 3. And I'm pretty sure it won't work, and I kind of don't need it to anyways, because if you notice, when I bring this over and put it under, that trinomial, that x squared plus 3x plus 9, is the same one that I just got in the numerator. So this full trinomial can divide out with that full trinomial because they are completely the same. So even though there's pluses in between those, because this whole factor is being multiplied by something else and that whole factor is being multiplied by something else, that's why I can do it. That's why I can divide it out. So now all I have is x minus 3 in the numerator and 3 in the denominator. Now for this one, because there is not an x in the denominator, there's no concern that the denominator will be 0, so I don't have a restriction on x. You can just say that x minus 3 over 3 is your answer. Last but not least, if we factor our numerator here, it does not have a GCF, so I'm thinking perfect squares or perfect cubes. And those are actually perfect squares, so we're going to get binomials. So x squared and 4, 1 plus 1 minus, which actually I have perfect squares again, but it has to be subtraction, so I can actually factor my numerator yet again. The positive one will stay the same, but the subtraction one, I can factor those perfect squares again for x and 2. 1 plus 1 minus. Now the denominator, because there are 4 terms, I'm going to do the unboxing method. So I'm going to put everything in a box. And then I want to think about rows and columns. So let me get a different color here. Looking at this first column, they have an x in common. Looking at this column here, they have a -2 in common. Looking at the rows, this top row has an x squared in common. And then the bottom row has a 4 in common. And I just want to make sure when I multiply that everything works out. So like x times x squared is x to the 3rd, -2x squared, 4x, and -8. So that factored to x minus 2, and then x squared plus 4. And so now because I'm a big old multiplication problem, I can look for common factors to divide out. So in the denominator, I had an x minus 2, and I also have one in the numerator, so those can go. In the denominator, I also have an x squared plus 4, and I have another one just like that, so those can go. And so overall, I'm just left with x plus 2. And again, no denominator, so no worry that it's going to be 0. All right, I'll see you on the next one.